Welcome back, my fellow assassins, to another episode of the Dark Assassins Podcast, the show that dives deep into not just technology, but the concepts, software, and procedures behind it all, and explains it so simply that even your grandma can understand it. As always, I'm your host, the Dark Assassin. Back in the very first year of this podcast, we did an episode on networking, and if I'm being honest, it was probably one of, and probably still is, one of my favorite episodes that we've done on the podcast. And as a matter of fact, I liked it so much that I cut out a decent segment of it, one of the ones about trying to download GTA 5 in the core module, or core modules, is that what I called it? I don't remember. The kind of the greatest hits series that we did, which I do plan to do more as we kind of go along in the show, but kind of make it more of a staggered thing, so I'm not dumping all the episodes at once. Just kind of layer in another part here or there. But the point of this is that episode was called "The Hardware That Runs the Internet," and that was episode 27. So if you haven't listened to that episode, I highly encourage you to go and do that after this episode, if you haven't done so already, or it honestly would just be a nice refresher if you want to go ahead and just listen to it again anyway. But this is sort of a sequel of sorts, where we basically dive into the stack that runs the internet. So I'm talking about TCP/IP, the TCP framework. So we touched on it briefly in that episode, The Hardware Runs the Internet, and we've touched on it in other episodes as well when we've brought up networking. But when we touched on it in other episodes, it's mainly been, here's the context for how this thing works, right? Like when we're talking about switches, yeah, they operate on, the data link layer, layer 2 of the TCP/IP model. Kind of give a little bit of context, but basically kind of leave it there. So for this episode, we're going to basically break down and walk through the creation, the network stack rather. We're not going to go super deep into the weeds, into the, this is how a network packet is constructed and dissect a network packet. That would probably be another episode in and of itself. But basically kind of like at a high-ish level, kind of diving into what each layer is, what it consists of, and what makes it, I guess. And it's basically, this is kind of one of those core episodes that is very important for anyone in the IT space to understand, because whether you're a network engineer, I hope you kind of know the network stack. If you are a software developer, it's also helpful to know the network stack, because if you don't know the network stack and you're a software developer, it's going to make writing network code a little interesting for you. You're not really going to get it, so I highly encourage that for software developers. But basically everything in IT these days relies somewhat on networking at some point, so having at least some kind of understanding of how they work is definitely beneficial. But before we dive too deep into that and get ahead of ourselves, let's start off with our trivia question for the week. So in the spirit of networking, IPv4 addresses are 32-bit numbers consisting of 4 8-bit octets, while as IPv6 addresses are much larger and combine 2 octets into one to form a 16-bit hextet. How many hextets are there in an IPv6 number? So again, how many hextets are in an IPv6 number? Now, as a little bit of a hint for you, if you listen closely in this episode, you'll be able to do some math and figure out the answer. But that is this week's trivia question. Now, moving right into, let's get into this week's cybersecurity tip. Now, this week's cybersecurity tip is to make sure you are sending messages over end-to-end encrypted channels when possible. Now, some government organizations might try to encourage you to do otherwise, But that is solely because they want the ability to see what you're up to and see what you're talking about to better monitor you. But it's not just the government boys that might be interested in what you're doing. Threat actors as well are always interested to get the latest juicy insider details on you, because if they get some insider information on you, that might help them with various kinds of social engineering attacks. It could maybe help them decipher your passwords depending on what kind of information you're unveiling to them and what else they can figure out about you. So it's not specifically, obviously, just governments, but it's always funny to bring up the governments when it comes to end-to-end encryption, because they like to play it rather fast and loose, and pretty much whenever it benefits them, they want encryption, but when it doesn't benefit them, then they don't want it. Like, it was kind of funny, within the span of a few months, you had the United States government telling everyone basically to use end-to-end encrypted channels for text messaging because the alleged Chinese hacker group Salt Typhoon was so deep into the American communications networks that they had no idea if they're still in there, and they're probably spying on you, so use end-to-end encryption to make sure the Chinese don't get your data. But then, on the other hand, they're also like, no, don't use end-to-end encryption because we want to spy on you. And that was very evident in the whole UK case that came out not too long ago. Well, I guess alleged UK case where allegedly, according to reports, the UK government basically demanded that Apple put a backdoor into iCloud to basically allow them to have access to the data stored in iCloud, because iCloud uses this thing called advanced data protection, and basically what that is an end-to-end encryption service that allows you to basically ensure that all your data going to and from iCloud and amongst other Apple Cloud services is all end-to-end encrypted, and basically the UK wanted a backdoor into that so they could basically get around it. So governments are notorious for wanting backdoors in encryption, and as we've talked about many times, that is a horrible idea. But getting in specifically to the end-to-end encryption, end-to-end encryption basically ensures that you and only you, well, I guess also the recipient of your messages, are the only ones that are going to be able to see those messages, because it's encrypted by you, sent across the wire, fully encrypted, and then only decrypted when it gets to your recipient. So it doesn't matter if your internet service provider, your cell phone company, your government is spying on you and intercepting all your traffic. If everything's end-to-end encrypted, all they're going to see is a bunch of jarbled garbage, and they're not going to be able to understand anything. So it's fantastic for privacy reasons, but also security against hackers too, because as we kind of touched on, hackers are always interested in trying to intercept any kind of data they can to gain any kind of insight into someone to see what they might be able to use and what they might be able to exploit in, say, like a social engineering attack, like a phishing scam. Because if they can identify things that you're particularly interested or have an affinity for, if they can tap into that and send you like a super personalized phishing attack, which is basically known as spear phishing, there is a much higher likelihood that they're going to be able to convert you into a victim rather than you just deleting it or it going directly into your spam folder. So, but the other thing that's nice about end-to-end encryption is just the peace of mind that it gives you, knowing that your conversations are private and only you and the person you're sending your messages to are able to read them. So you don't have to worry about, hiding details, unless I guess you want to hide details from the person you're talking to. But you don't have to worry about, trying to hide something because you think that maybe someone might be reading your messages as you're saying it, so you don't want to give out too much information. Now, when it comes to choosing an end-to-end encryption app, you obviously have to kind of do your own research on some of the options out there, but some of the most notable ones is iMessage. So if you are on an Apple device, if you have an iPhone, iMessage is great for that. It's end-to-end encrypted. Assuming, of course, you're messaging other people that are using iMessage, because it also should be worth noting that just because you have an iPhone doesn't mean you're using iMessage, because there is a way in messages that you can disable iMessage for whatever reason if you want to do that. I don't know why you would, but it's technically an option. But iMessage is a great one, end-to-end encrypted automatically. Another one is WhatsApp, which personally, since it's basically a Facebook, or a Meta product, by principle, I will never use it because it is a product by Meta, but it is a very popular option when it comes to an end-to-end encryption messaging platform because it does use end-to-end encryption by default. And then the last kind of big one I wanted to touch on was Signal. Signal's been known for a few years now about being very privacy-focused and having a very strong security and privacy model with end-to-end encryption kind of at the core of their business model, I guess. But as a quick reminder, we kind of alluded to it a little bit there with iMessage, but just because apps might offer end-to-end encryption, like iMessage, for example, that doesn't necessarily mean everything's end-to-end encrypted. So, for instance, if you're using messages on like an iPhone, you're using iMessage, if you're texting with, say, like an Android person and the messages are SMS messages, those are not encrypted. So just because you're using the Messages app on an iPhone that uses iMessage doesn't necessarily mean that everything's encrypted. So if you're dealing with any sort of SMS, that is not encrypted whatsoever, so it's just something to be mindful of. So yeah, don't let your conversations fall into the wrong hands, and make sure that you are using end-to-end encryption to keep your chats private. And that is your cybersecurity tip for the week. Now, moving right along, let's get into what nerdy stuff have I been up to this week. So I actually got back to a little bit of nerdy things. Not a whole lot, but a little bit. So I made an update to my Server Connect program, which is a program that which, to be honest, I haven't really touched this program in, I think it's been close to a year, if I recall correctly. I think the last GitHub release, I think, was back from like May of last year, I think. But that's basically just how it goes with this project. Like, I don't touch it for a while, and then I start using it, and then I find some case that I'd be like, it'd be really nice if my tool was able to do this, so then I go ahead and add it. Now, there was a couple, in addition to adding features, I did add, like, I guess, a quality of life measure, if you will. So I made it more resilient to quote-unquote crashing. And basically what I mean by that is, in certain cases, like where it would prompt you, like just kind of like a yes or no prompt, like if you want to continue or something, and you hit Control-C, it would basically look like it's crashing and erroring out on you because it's not handling the keyboard interrupt properly. So basically, just to kind of clean up the output, I basically added a bunch of different try except statements inside the program to basically catch those various Control-C statements, those keyboard interrupts, and basically handle and exit gracefully. So that was not really necessarily a necessary update, but just kind of more of a polish, I guess, update. And then the major update that I actually implemented was removing the SSH fingerprints when you delete a connection, or at least giving you the option to. Now, basically, the reasoning for this is, if you have a home lab and you frequently change devices' IP addresses around, you'll undoubtedly run into a situation where SSH will basically yell at you and panic and not work if you try to SSH into a server that was previously a different server and the SSH keys are different. Now, don't get me wrong, this is a fantastic security measure to make sure that you're not unknowingly logging into a different device that you don't intend to. So it is a fantastic security measure. But when you know that the device is legitimate, it's just kind of annoying. So the thing of it was, like, when you would delete a connection, sure, the connection was gone and you wouldn't be able to, use the script to connect to it anymore, but it didn't do anything with your SSH fingerprint. So if you re-added a new, server with that same IP address, you would kind of run into issues. So basically the point of this script was to update it so if it would basically prompt you, do you want to remove the SSH fingerprints? Obviously you could say no, but it was basically just a quality of life improvement. Now, another kind of on the flip side, when you add or when you log into a server for the first time, it always prompts you like, hey, do you want to accept these SSH fingerprints? So I didn't actually implement this yet, but it's kind of another idea that kind of popped into my head, is basically add a feature flag or something that basically will allow you to auto accept fingerprints for either a single connection or all of your connections based on, what arguments you pass in. Which it's kind of funny in that sense, because for basically a year, I had nothing in regards to updates for this script or program, and now I'm just coming up with new ideas, which I guess, to be fair, I did have this idea to remove the SSH fingerprints for a while now, like for a few months at this point. I don't know how long it's been kind of sitting in my project ideas as part of a thing I should update, but just kind of never really got around to it. But it was something I wanted to update for a while, just like I said, never got around to it. But now I have this other idea that I want to update. So assuming I actually get around to it soon, it's kind of funny that in 1 year there was basically a single update, and then within the span of, I don't know, maybe a month, couple weeks or something like that, there's 2 updates. But, that's just how it goes with this kind of a personal project, where you're not doing it because you want to, drive a user base. You're basically just using it as a tool that you use for yourself, and also decided if anyone else wants it, they're more than welcome to have it. So that was that. And then I touched on, I think it was last week, how my home lab was basically the bare minimum in regards to setup. But this week I finally got around to adding some more devices back into the picture. So specifically, I hooked back up my 2012 Mac Mini as well as my other, shall we say, development Mac to basically help me transition my apps to Apple Silicon, we'll say. So got those hooked up, just basically made sure that they were connected and working, and that was basically the extent of it. So yeah, that was what I got up to this week. But with that, let's move into the main topic for this week's episode, which is networking, specifically the TCP/IP model or the TCP/IP framework stack, whatever you want to call it. So one of the best ways to kind of analogize this, which we're going to come back to a few different times over the course of the episode, is basically this idea of the post office or the delivery service. It's a really good analogy, and you'll kind of see that as we walk through each of the layers. But it's a little bit of context. So the origins of the TCP/IP model kind of developed in conjunction with the ARPANET back in the 1970s, which the ARPANET was kind of a very kind of like the precursor to what we know now as the internet, which the ARPANET and the story of the ARPANET is basically, an episode for another day. It basically deserves its own episode. But the emphasis of the TCP/IP model compared to, say, the OSI model, which is very similar, is the TCP/IP model is more of a practical model, more built in the real world, compared to the the OSI model is very much kind of a theoretical in practice type of a thing. But because the TCP/IP model was kind of built alongside, the actual kind of development of the actual internet, or I guess in this case the ARPANET, it kind of made sense that that's kind of how it developed, and they kind of molded it to fit, as they were building it out. So basically the kind of some of the main points of creating this model in the first place was, purely for standardization purposes, because if you want more devices to be able to connect to one another through this thing called the internet, you have to have some sort of standardized way to allow them to do that, because otherwise, how are they going to communicate, right? Like if I'm not using a MAC address for my network interface and I'm using something completely different, and I'm not using IP addresses, I'm using something else completely different, how am I going to be able to communicate to the rest of the network, right? So one of the big points was for standardization. And the other benefit to it too is the kind of layered approach, and which basically allows for kind of different layers of modularity. So for instance, like when you're talking about network switching, for instance, like network switches. You don't really have to worry about some of the higher levels of, or layers, I guess, the higher level layers of the network stack, because you only have to basically concern yourself with the MAC addresses, which we'll kind of get into. And based on the MAC addresses, you can easily identify, where you need to route packets to, and it makes it a lot quicker and more efficient because you don't basically have to dismantle the entire packet in order to do that. So, yeah, so basically the point of the TCP/IP model is just to kind of give that architecture for the internet. So we talked about the different layers, so let's go ahead and break those down. So first we have the physical layer. Now, depending on who you talk to, the TCP/IP model doesn't actually contain a physical layer. There's only 4 layers, and you basically have the data link layer that basically combines both of them. But personally, I like kind of dividing them up into the physical layer and the data link layer because they are technically different layers. So the physical layer, kind of as I said, it is kind of debated depending on who you're talking to. But the idea of the physical layer is the transmission media. So, this is your Ethernet cabling. This is your, Wi-Fi radio waves. Your basically everything can relating to how the data is transmitted. So whether that's fiber optics, kind of radio waves, as we touched on, other things too, like the bandwidth and different signal strengths for things like that. That's all kind of included in the physical layer as well. And kind of at the core of it is basically anything dealing with electrical signals, right? So the electrical signal to send the data through the wire, whether if you're dealing with Ethernet or sending the data through the airwaves, if you're dealing with Wi-Fi, for instance. So these are basically what consists of the physical layer, things like the bandwidth, the bit rate, signal integrity, things like that is what's kind of included in the physical layer. So then moving up from that, we have the link layer or the data link layer. And this is where you kind of get your addressing, your MAC addressing, which we've touched on before. So MAC addresses operate at the data link layer, which is also similar if you want to kind of compare them to the TCP/IP model to the OSI model. Both of them have a data link layer. They both serve the exact same purpose, basically dealing with MAC addresses for local network communication. So kind of as we touched on, if you have like a network switch, that's operating on the layer 2 level because it's basically just dealing with MAC addresses. Depending on the switch you have, the switch might not even have the awareness of what an IP address actually is. Now, if your switch can do things like layer 3 routing, which we'll get into in a second, then it obviously is aware of IP addresses. But otherwise, it's basically solely dealing in MAC addresses, which is why, one of the reasons why, if you can operate things solely on the switch without having to go up, say, to your router, you can achieve decent speed up in performance because you're just dealing with that MAC address layer. You're dealing with a lower level, and it's pretty fast in that regard. So I guess we've talked about MAC addresses, but what actually is a MAC address? So a MAC address is a hardware-based thing, and it's burned into the network interface card during the manufacturing process. So anything that can connect to the internet has a network interface card, whether that's kind of like a Wi-Fi card or a like Ethernet port on it, an RJ45 connector. Each one of those has a MAC address that's basically assigned when it's manufactured. And technically, they're not changeable, but there is ways in software that you can basically spoof your MAC address and change it to whatever you want it to be. But the point of MAC addresses is basically it's unique and it doesn't change, and your average user of a computer or phone or whatever is not going to be changing their device's MAC address. It's just going to be the same throughout the lifetime of the device. So it's it's a 40-bit unique identifier. So it's basically a 40-bit hexadecimal number. If you've probably seen them before. It's basically 2 numbers followed by a colon. Well, maybe numbers, maybe it's hexadecimal. So technically it's all numbers, but to the human eye, it looks like a combination of numbers and letters. So kind of an example MAC address, this wouldn't be legitimate, probably, but would be something like 00:1A: 2B: 3C: 4D: 5E. And basically what this means is there's theoretically billions of unique MAC addresses, but in practice, that's not really the case, because if you actually dive deeper into the MAC addresses, you can actually kind of decode them a little bit. And the first 24 bits of the MAC address actually represent the manufacturer that created it, which is why you can sometimes notice if you have multiple devices from the same manufacturer, like the prefix of their MAC address, or kind of like the first majority part of the MAC address is basically the same, and then it's just kind of like the latter half of it that differs, and that's basically the reason for it, is because the first part of it is basically telling you who created it. And I'm pretty sure there's like websites that you can actually check this, like you can actually look this up on, is you can see like who actually was the original manufacturer of your address, which is pretty important if you actually want to get into MAC address spoofing, because you have to also kind of make sure you can't just pick you can't necessarily just pick a random MAC address, because you kind of also have to make sure that the first part of it actually aligns to a legit like manufacturer of a MAC address. So if you're trying to spoof a MAC address, there's kind of a helpful tip for you, is make sure the first part of it is actually tied to like a legitimate manufacturer. So I guess kind of a helpful tip if you're in the market for spoofing your MAC addresses. Now, how do MAC addresses actually work? So kind of as we touched on, they're tied to a network interface card, or a NIC, by the manufacturer. And it's a unique identifier for each NIC. And basically how MAC addresses work is they work on the broadcast domain and are basically used to identify other devices on the same network through the broadcast domain, which we'll get into a little bit. If you've heard of the broadcast address, is basically the 255 thing. So if you want to like kind of send a blast message to every device on the network, which I guess 255 is very much dumbing it down, because depending on what your subnet is, which we'll get into what a subnet is, 255 isn't necessarily your network's broadcast address. But the point is, when you're dealing with the broadcast domains, the MAC address is basically what you're after. Like when you're sending out the ARP packets, or the address resolution protocol. That's, if you've looked at any kind of Wireshark data capture, you'll see a lot of these ARP packets being thrown around, like, hey, who has this IP address? I have this IP address. Okay, who has this IP address? And it's basically allowing the different devices to be able to identify on the layer 2 level, what MAC address is tied to what IP address and whatnot. But also, as we've also touched on the layer 2 level, is where switching comes into play. So when the switch receives one of these packets or one of these frames, it basically examines it to determine what the destination MAC address is in the frame header, and then it's able to look up the MAC address in its MAC address table and then forward it along to where it's supposed to go. So it doesn't have to go through the entire process of taking the entire packet apart. It basically just has to look at the very header part of the frame, and it can identify the MAC address. And because switches are fast and they have their various lookup tables of what MAC address is tied to which port, they can easily forward those on, and it's a lot quicker than having to go up another layer to the network layer and have the router do the same thing and then forward it along that way. A lot less steps, a lot less hops, so it's a lot quicker, more direct. And then, as we touched on, there's the address resolution protocol, which is basically how devices communicate with one another on the same network to identify which IP address resolves to what MAC address. So this is kind of where the post office analogy really starts to come into play. So if you think of this, in terms of the post office, your IP address is basically the city or the state that you live in, assuming you're living in the U.S. And it basically tells the post office which network or which distribution center to initially send the data to, send the mail, send the letter, send the package, whatever. But then your MAC address is like your physical street address. So something like, 324 Roundhouse Lane. Shout out to the couple people that actually got that reference. And it's basically permanently assigned to your house and is used for the local delivery. So the letter basically uses the IP address to get you basically to the right area. And this will make a lot more sense when we break down the difference between public and private IP addresses. But the IP address basically tells you where to send it to, and then the MAC address tells you exactly where it's supposed to go in that general vicinity. And like I said, it'll make a lot more sense once we get to public and private IP addresses, which is in the network layer, which happens to be the next layer up. So this is kind of where the key part of the routing infrastructure of the internet comes into play. It operates at the network layer. So this is where IP addresses come into play. So we've kind of already touched on them a little bit, but just like a MAC address, they identify devices on a local network, and they also can identify networks in general. So if you think of the internet as a whole, for instance, on your local area network or your LAN, you'll probably have a range of IP addresses that start with something like 192.168.1. something, and all of your devices in your house have an IP address kind of in that general range, and that's what's considered a private IP address. But then if you try to go out to the public internet and you say you type into your favorite search engine of choice, what is my IP address? You're going to see a number that is very different than what your laptop, desktop, iPhone, Samsung Galaxy, whatever, says your IP address is. It's going to be very different. And that's because that is your public IP address. And the public IP addresses is kind of what we touched on there. IP addresses are used for identifying devices on any network, or basically networks in general, because as we're going to see here, IPv4 wasn't designed to have all of the various devices on it that exist in the world today, so we had to come up with some very creative solutions for how to deal with that. Now, specifically talking about IPv4, kind of like we touched on in the trivia question, they're 32-bit numerical addresses. So they're basically a 32-bit number, and they're broken up into 4 different octets, or basically 4 8-bit numbers. And kind of it's a dotted decimal notation, so kind of like I touched on, it's your 192.168.1.5, right? That would be an example of an IPv4 address. Now, there's a little bit of a difference between IPv4 and IPv6. Now, IPv6 has been around for a few years now. It's kind of been around for a while, actually, but hasn't really gained much widespread adoption. And probably for decently good reason, because kind of around the time where IPv6 really kind of got created, we kind of got pretty good at subdividing up IP addresses, and we kind of came up with this idea of a public versus private IP address thing. We came up with things like NAT, or network address translation, and we came up with a bunch of different ways to basically resolve the issue that IPv4 did, which it's limited to only being able to have just over 4 billion addresses, which is kind of comes with the territory of being a 32-bit number. So in our digital age, it's not necessarily a lot when you consider how many devices everyone has, right? There's more than 4 billion people on this planet, and I can almost guarantee you that maybe not everyone has more than one device, but there are a lot of people out there, myself included, that have more than their fair share of devices that have an internet connection. So each one of those having a unique IPv4 address, you quickly realize that there aren't enough of them to go around, basically, which is why if you actually are interested in buying a block of public IPv4 addresses that are routable by the internet, get ready to shell out a fairly large chunk of change depending on how many addresses you want, because they get pretty pricey pretty quick. So just kind of as a heads up there. Now, when we're talking about home labbing type stuff, IPv4 is definitely the way to go because it'll make your life a heck of a lot easier. Now, IPv6 was basically supposed to be the solution to IPv4 because it was rather than a 32-bit number, it was a 128-bit number. So rather than having just over 4 billion unique addresses, it can have 2 to the 128th power addresses, which comes out to around 3.4 times 10 to the 38. And no, I'm not even going to try to pronounce that, but it's a lot. It's basically, I think, gets into the number above like decamillion, so basically 11, whatever that number is, and then a bunch of others. So it's insanely large. So theoretically, I guess, everyone in the world could have a unique IP address for each one of their devices. But personally, I don't think that's a very good idea, because the number of hackings would probably skyrocket, because as we've seen from just the number of devices that are public facing, people's ability to keep their software and devices up to date is pretty bad. Also, you factor into that IoT devices, or Internet of Things devices, which are known to be a haven for botnets. Botnets love hacking IoT devices because how horrible their security tends to be. So having things like that connected directly to the internet is just a disaster waiting to happen. So personally, I don't think it's a great idea, which I think is probably why people are still tending to stick to the whole idea of a public-private IP address scheme, where basically you get a public IP address assigned to you from, say, your internet service provider, and then based off that public IP address, all of your devices locally can essentially share that IP address. Now, there are things like CGNAT that basically you don't necessarily get a dedicated public IP address, so this can be kind of annoying if you're trying to create a VPN tunnel into your home network, because you don't exactly have a public IP address that you can route into. But I think we've talked enough about the whole kind of public-private IP address thing that we should probably kind of actually get into what I actually mean by that, because I kind of touched around it, but haven't really dove into it. So the point is, kind of as I touched on, it's everyone that is on the public IP space has their own public IP address, or a globally unique identifier that's used to connect to the internet, and is essentially, because we're talking about a public-private IP address space, it's basically, think of it in essence that each public IP address is its own network. Now, that's not a hard and fast rule, because, for instance, if you go to any kind of like cloud provider and set up, say, like a virtual machine in the cloud, most likely that virtual machine is going to have a dedicated IPv4 address, and it's obviously not, its own network beneath it serving a bunch of other devices. So things like servers, out on the public internet, it's kind of a bit of a different case. But kind of the idea still applies, in the sense that if the IP address is a publicly routable IP address, then it is accessible via the internet. Now, when they designed IPv4, they created a kind of a different segments of public and private IP addresses. So one of the main blocks of private IP addresses that most people are familiar with is that 192.168 number. And then you can basically pick the last two dots to essentially be whatever you want, and those are, private IP addresses. So they're not publicly routable on the internet. Another common one is the 10 dot network. So if you do like a 10 dot something, that would also be one. And then I believe the other one is it 172 or 127? Well, 127 would be like your local host. So there are things like that. So that's kind of like the main difference. So you have some IP addresses that were specifically dedicated for use in, private networks, right? Like a local area network. So all of your devices on your, on your LAN would be able to have their own IP address, but also be able to share the singular public IP address. And the way that now this kind of begs a question though, because right, if everyone has the same public IP address, like if I'm on my laptop and I'm on my phone and I'm both browsing the internet on both of them, how is it that my phone only gets messages and data meant for the phone and the laptop only gets data meant for the laptop? Because if you think about it, if the whole idea of the IP address is basically to tell the packet, where to go, how do you distinguish between a packet that was sent from your phone coming out of the public IP address versus the laptop coming out from the public IP address? Because from the broader internet perspective, it's the same IP address asking for these resources. So how do you distinguish which goes where once it gets back to your public IP address? And that's where routers and network address translation comes into play. So network address translation is basically how your router is able to determine where packets are supposed to go within the internal network. So from your computer and phone's perspective, their local IPs are their actual IPs. Because if you can see this when you actually look, if you do like an IP config or an if config in the terminal, you can see like the IP address. So from your device's perspective, that is its IP address. But since that obviously isn't directly connected to the internet, you have to go through your internet gateway, which is basically your router or your access point or however you have your network set up. So since all of this internal network traffic, in order to get out to the public internet, has to go through this singular gateway, aka your router, that's basically where the magic happens. So the router is able to keep track of all of the various connections coming into it. So it's able to see, what port and what, I think it's mainly based on the port, but it can basically, when you send a connection to the router, like, hey, I want to go to, say, this address, your router can make a note of that in one of its various tables. And then, same thing with your laptop. It wants to go out to connect to a different service. It goes out, and then when the router receives traffic back from one of those services, it can basically do a lookup in its table and identify which device on the local network it's supposed to go to in order to properly route traffic accordingly. So that's in essence how network address translation works. So basically when the data comes from an outbound connection relating to one internally from like a previous setup connection, like when you're browsing the web, for instance, and you say you enter a new URL you want to go to, that's where the router is able to keep track of that. It knows which private IP address is associated with that connection and can handle it accordingly. So this is kind of getting in. So now we've kind of already touched on routers. So this kind of gets us into the next portion of IP of the layer 3 part of the network, which is routing. So basically the process of getting IP or packets from their source to its destination. Because obviously, if I'm trying to connect, which actually you can actually do this if you want to do if you do like an NS lookup, you can basically see like the various hops that your network packet takes in order to get from your device to wherever you're trying to connect to. And the way that this is done is through routing tables. So basically what happens on the internet at large is every single router that's connected to the internet is constantly forwarding packets to one another. And they have these various routing tables to basically look up where the next hop is based on whatever algorithm they're using to identify what is the shortest path to get their packet where it's supposed to go. So when your router receives a packet from the broader internet, if it's not meant to go internally, it then does a lookup in its routing table to identify where else it's supposed to forward that packet along and then forwards it out. So how this works is, so like I said, if it's meant for, a packet internally, like it was forwarded to your router and your router see that it's meant for internally, then it can use something like network address translation to handle that accordingly. But the way that these routing mechanisms are done is through either a static or a dynamic routing. So basically the main thing, the difference here is static routing. Obviously, you define the specific route. So if I get, anything related to, say, this IP address goes here, or anything related to this IP address goes there. And you basically predefine and statically assign those things, kind of like a static IP address, rather than using something like DHCP, where you basically just reach out and say, hey, give me whatever IP address is available. Here you go. A static IP is your IP address is always set to that thing. Static routing is kind of similar in that sense. And then you have dynamic routing, which uses things like various protocols or algorithms or whatever to basically automatically learn and update the routing table accordingly. So then kind of also on the network 3 layer, or the layer 3 layer, the network layer, you have subnetting. Now, we've talked about subnetting before on our VLAN episodes, but essentially what subnetting is it's a technique used to divide a network into smaller, more manageable chunks. So the most common one of these is the /24 network, or basically if we go back to the 192.168 IP, it would be 192.168.1 to 254. And the reason why it goes to that is because you have 0, which is assigned. So you basically have two addresses that are a loss. One is for the address itself for the network, and the other one is the broadcast address. And the reason why subnetting is so important is it's great for not only efficiency reasons, but also for security reasons as well, as we kind of touched on our VLAN episode, or virtual local area networks. And VLANs, in essence, that's basically all they are subnets, and then you have your various ways to traverse between those networks, or those subnets, because they are their own individual networks, and you have different means of traversing through them. And as we touched on, the /24 is the most famous one. If you're looking specifically at the net mask, that's usually the number that looks like 255.255.255.0. If you see that, that's basically just the net mask telling you that you're on a /24 network. Now, there are tons of different networks that you can talk about, basically anything from 0 to 32. So you can have a /20, a /30, a /16. And the bigger the number, the smaller the number of IP addresses you can have. So a /25 network will have less IP addresses available to it than, say, a /16 network. So for the average user, though, none of this probably really matters at all, and you're just going to use the /24 that comes default on your router that your ISP gives you, and you're just going to call it a day. But if you are one of those people that I talked about that wants to have your own allocation of publicly addressable IPv4 addresses, you're probably going to want to have some way of subdividing those out if you want to, say, lease them out because you want to be your own cloud service provider or whatever. Having some way to lease those out in smaller chunks through subnetting is a fantastic way to do that. And also, if you want to set up, VLANs for your home network for more kind of, network segmentation and security reasons, it's also a fantastic thing to do for that as well. So the next layer up is the transport layer. And the transport layer is basically kind of the heart of the TCP IP model. And that's kind of where the TCP, in essence, kind of comes. Well, the TCP in this context is the transmission control protocol, but we're getting a little ahead of ourselves. TCP is essentially where the end-to-end communication of applications lives. So it's above the network layer, and this is kind of, depending on what you're using, this is kind of where you can either opt for speed in the sense of UDP, but not necessarily much reliability, or go for TCP and have that more of a reliable delivery mechanism. So this is the layer that basically handles the sequencing, error detection if you're using that, and control flow to ensure the data arrives correctly and in the right order. And this is where TCP comes in. Now, TCP is probably the main type of connection you're going to be using when you're doing any kind of network-based communication. Now, obviously, there are exceptions to this if you're using something like a streaming service or any kind of service where you don't necessarily care if you drop some packets, or you don't care if the person on the other end is even listening. Then you would obviously opt for something like UDP, which is the user datagram protocol. But TCP is the one that basically is connection oriented. So basically what that means is it establishes a connection through a dedicated connection protocol before data transmission even begins. And it's a way to basically ensure that you have a reliable stream of data. So how TCP accomplishes this is through a three-way handshake. So basically how the three-way handshake works is first you send out the SYN packet or the synchronized packet, and this is basically the client sending the SYN packet to the server, basically requesting a connection. And then the server will send back a SYN-ACK packet or a synchronized acknowledgement packet. Basically, the server is saying, like, yes, I hear that you want to create a connection and I'm good to go, basically acknowledging the request and basically telling the client to initiate the connection. And then you have the final packet, which is the ACK packet from the client, which is basically the client telling the server, hey, I got that, and we can go ahead and start communicating. Now, this is where a common, paradox comes in that often gets brought up when talking about the TCP protocol, and that is the two generals problem. Now, if you haven't heard of the two generals problem, it's a very interesting thought experiment. So basically how it works is you have two generals, and they're trying to communicate with one another, whether it's they're trying to, organize a battle strategy, whatever the case is. But essentially, one of the generals wants to send a message to the other general. So they send a soldier over the mountain, across the stream, through the forest, whatever, to the other general to deliver the message. And how does that general know if the soldier actually delivered the message or not? Well, if the second general sends the soldier back or a different soldier back, basically telling the first general that they received their message, then the first general knows that their message has been received. But the problem is, how does the second general know that their response messenger actually made it there to tell the first general that their message was received? Well, if the first general could always send a soldier back to the second general, basically telling them, hey, I got your message, we're good. But then how does the first general know that that soldier made it in time? So then the second general can send another soldier, and you basically get into this endless loop of how do you know that the soldier actually made it there, and that is in essence the two generals problem. Getting back to TCP though, one of the kind of reasons why TCP is so beloved and so widely used is because of its reliability features. So some of these include things like sequence numbers. So each byte of data that gets assigned its own sequence number. And this is important because if for whatever reason a packet gets dropped or data gets sent out of order, it doesn't matter because every byte of data has its own sequence number. So when the client or the server, whoever's receiving, gets the data, even if the data shows up out of order, because everything has a sequence number, they can then reorganize it into the proper order and ensure that the data was received correctly. And then, of course, you have the acknowledgement. So basically, as this receiver is receiving data, it will send acknowledgement packets to the sender, basically confirming that, hey, yes, I did receive this message. And then, of course, you have the retransmission aspect. So if for whatever reason data packets get dropped for whatever reason, interference, overloaded network, whatever the case may be, you can then retransmit those packets to ensure that everything arrives appropriately. And this is why TCP is so great. And in contrast to UDP, which, as I mentioned, is the user datagram protocol. But as we kind of touched on with TCP, if you're looking for the most high-speed type of connection between a client and a server or a peer-to-peer, TCP is probably not the way to go, just because unless reliability is the most important thing. The problem with TCP is, as we touched on, there's a lot of overhead that's involved with TCP communication because you have all these packets going back and forth, basically acknowledging that you received the packets. If things have to be retransmitted, that's additional, network traffic, adding the sequence numbers, to reassemble everything accordingly. There's a lot of overhead involved. But UDP, on the other hand, is basically the complete opposite. The best way to describe UDP is fire and forget. You don't care if the person on the other end is even listening. You're just blasting out messages as fast as you can and just sending them off. You don't care who hears it. If anyone's listening, just fire them off. So obviously TCP is a lot more reliable, but UDP is a lot simpler because, like I said, there's none of this, reliability mechanisms built into it. It's just shooting off the messages, so it's a lot faster. And if you're interested in doing anything like a streaming service, or it doesn't necessarily matter if you drop packets here and there in the middle of things, UDP is without a doubt the protocol that you want to go for that. Now, the reason why a lot of people tend to not go with UDP for more, critical type applications is because of the unreliability, and essentially there's no guarantee of delivery of any individual packet. And obviously, if you're sending a file over the network via UDP and a couple of the packets don't make it, you're going to have some data corruption, which obviously isn't good. But like I said, for any kind of application that's like, kind of a live type of a thing, like game streaming, video streaming, things like that, that is where UDP absolutely shines in its use case. Now, when it comes to TCP, though, there's a couple of different things kind of working behind the scenes, because TCP doesn't just blindly send data. It has various different algorithms involved in order to prevent overwhelming the network, and these algorithms are basically able to dynamically adjust the send rate based on network conditions. And one of these algorithms is kind of known as the slow start algorithm, which basically how this works is it initially, the sender sends data at a much smaller rate and then gradually increases it over time until it detects network congestion. Now, I'm almost certain every single one of you has seen this in action, because if you have had a direct connection to, say, another computer, a network share, or whatever the case is, when you initially start a large file transfer, you'll notice in the very beginning, your transfer speed is always very slow. And then as you kind of just begin the transfer, the speed increases more and more and more until you reach whatever cap is available to you. Typically, that's going to be like a gigabit type speed. Or if you're a baller, maybe it's 10 gig or even faster. But basically, that's why when you start a file transfer, initially the transfer speed that you see there is always significantly lower than what the max connection speed possible is. Which is also why if you transfer a bunch of small files, it's typically very slow, because you're never able to actually fully max out that transmission speed, because you're basically creating a new TCP connection and you have to slowly ramp up. But by the time you start ramping up, the file's already been sent. So then you start back at the beginning again, slowly ramp up, the file's been sent, and then it's a very slow process rather than allowing you to just transfer large chunks of data at that max speed. So congestion avoidance is another one, which basically this just detects usually through something like packet loss. If there's a lot of files or a lot of packets starting to be lost, then the sender is able to reduce their speed at which they're sending packets to hopefully alleviate some of that congestion to not have to retransmit as many packets. So that is the transport layer 4. And last but not least, we move into the application layer, which is layer 5. Now, this is the layer that basically everyone that works in networks, specifically software developers, is going to be working in. While you're using the TCP protocol or you're using UDP, your implementation of networks is at the application layer. So the application layer, of course, kind of as we've alluded here, is the topmost layer of the TCP IP model, and it's basically the interface between the network and the user's application. So this is where all of your applications you know and love exist. This is where your web browsers exist, email clients, file transfer programs, SSH, all that good stuff, they live in the application layer. This is why if you look at, what ports are available, like if you want to, say, open up the SSH port on your router, which you definitely should not do, but that's why it's assigned to port 22, because that's what the SSH protocol uses for its communication. So basically every application that operates on the application layer typically will have a port associated to it, or sometimes multiple ports for how it communicates its traffic over. Now, this layer doesn't handle the physical transmission of the data, but instead it basically provides the service or APIs that the application uses in order to communicate over the network. Now, and the way to kind of think of this is if you're, developing your own, web server, say you're developing a weather server that hosting weather data, and you want to you want users to be able to connect to your service through the network to be able to get weather data. You obviously have to have some way for those users to be able to connect to your service and pull that weather data, and that's where the APIs come into play, and that's kind of this layer 5 network idea. So we kind of already touched on some of the applications that exist here, but just to kind of hit the highlights of some of the key protocols here. One of the most famous is HTTP and HTTPS, which is the Hypertext Transfer Protocol. And this is basically the foundation of the web, not the internet, but the web, because they're two different things. Just so we're clear here, the internet is every traffic that exists, online. So this is not only HTTP traffic, but also email traffic, SSH traffic, VPN tunneling, anything that goes on is the internet, whereas web traffic specifically is basically anything related specifically to the HTTP and HTTPS protocols. So this is, web pages being transferred from the web server to the web browser, things like this. It's a stateless protocol, which essentially means that each request is treated independently from one another rather than a continuous stateful protocol where, based on what you sent before will kind of indicate how, the service will handle what your next one is. The next one is the SMTP protocol. Well, I guess that's redundant. Simple Mail Transfer Protocol. This is, your emails, sending and receiving emails between servers. And it's a very reliable protocol for ensuring messages get delivered correctly. Then, of course, you have one of the most famous ones for us home labbers, which is SSH, or the Secure Shell Protocol, used for securely sending commands to another computer, basically giving you command level access through a remote access or command line access on a remote system, basically allowing you to manage the system remotely. And everything through SSH is encrypted, so you don't necessarily have to worry about hackers or the government eavesdropping on what commands you're sending. And this is kind of the successor to the previous protocol that was used for managing servers, which was Telnet, which is basically the same thing. It works on port 21 rather than port 22, at least as the default port. But Telnet is not encrypted whatsoever. So if you're still using Telnet to manage your services and servers, please upgrade to SSH. And if your servers don't support SSH, well, I don't know what to tell you, but you should upgrade your servers to use SSH, and if your reason for we can't do that because our applications rely on these servers that don't support SSH, update your programs. I don't know what else to say. You should not be managing servers using Telnet. SSH is definitely the way to go. Now, if you are a home labber, you have most assuredly used SSH before. I guess unless also if you listen to the podcast, you've almost certainly used SSH, I would think, since most of you probably either have home labs or maybe you manage infrastructure as your professional day job. I don't know. I guess unless, of course, you're an entirely Windows shop, in which case I'm very sorry. And then the next protocol we have is FTP, which is the File Transfer Protocol. This is basically used for transferring files between computers over a network. There's also SFTP, which is basically the same thing but with encryption. Then you have DNS, which is the Domain Name System, which basically translates human-readable domains like DuckDuckGo, Google.com, Apple.com, Facebook.com, whitehouse.gov, all those various domain names into IP addresses, which computers can actually understand and then locate on the network. So one of the things we touched on briefly with HTTP was this idea of stateless versus stateful. And I want to go into that a little bit more here. So one of the reasons it's kind of important to understand is if you do want to create your own protocol, it's important to kind of decide during the development process how you want your architecture to be. Do you want a stateless protocol like HTTP, or do you want a stateful protocol like TCP? So HTTP, kind of as we touched on, is a stateless protocol because each request is independent from the previous requests. So the server doesn't retain any information about the client's previous interactions. So basically, when you go to a server saying, hey, I want your main web page, the server will be like, cool, here, this client wants the web page, send it off. And then maybe the next cycle or whatever, the client responds back, hey, I want this image. Web server's like, here you go, here's the image. And it basically doesn't care at all what you previously requested from it. It just sends whatever you're currently requesting, and that's it. But then you have stateful protocols. So this is basically where the server maintains information about the client's connection and previous interactions to allow for more complex and efficient communications. Because it would be pretty terrible if you were creating some kind of chat server to allow people to communicate with one another, but the server would basically forget everything that you sent to it to send to the other person. So if for whatever reason, say you logged out of the chat room and closed it out and all the text that was previously on your screen vanished and you tried to relog back in and none of that data repopulated itself, that would be pretty bad. Or maybe that's good. I don't know. I guess it depends on how you want your feature set. But stateful protocols can be very important. Like, kind of as I mentioned, you can have a lot more complex interactions and communications going on between the client and server if the server is able to remember various things about previous interactions with the client. For instance, if you were trying to, deliver accurate results to the client, and previously, you kind of kept track of whenever you sent, say XY result to the client, they always completely ignored it and tried to search for something else. Then you might know not to send that to them next time because they're probably just going to ignore it anyway. So the kind of things like this allow for better and more complex communication between the two. So then another thing we touched on here is the role of APIs, so, application programming interfaces. So this is how, networks allow, communication between one another. So allowing applications to interact, with the network. And these can basically define anything from the format of messages to how services can be accessed. So, as we kind of touched on, if you were to write your own service to serve weather data, you obviously need some sort of way for clients to be able to access your server and request weather data. And that is, of course, where the API comes into place in order to fill that role. So that is the TCP/IP model, 5 layers, and for the last little bit of time that we have together here, which I know we're kind of running a little bit long, so I'll try to make this a little brief, is the difference between the OSI model and the TCP/IP model. So the OSI model stands for the Open Systems Interconnection Model, and it was developed as a theoretical framework for network communication and is very, very detailed and has more layers than the TCP/IP model. Essentially what it does is it takes the application layer and breaks it down even more granularly into different layers. So where the TCP/IP model, on the other hand, is a much more practical model that reflects how the internet actually works. And, the layers, more or less, kind of as I said, have basically the same name. So if we go 1-for-1 OSI versus TCP/IP model, the OSI model, you have the physical layer, which is the same as the TCP/IP model, which is the physical transmission of data. Then in the OSI, you have the data link layer, which is the same as TCP/IP, which is, for routing and addressing, the MAC address and switching type of a thing. Then you have the network layer on both, which is the same, and that's, your IP addresses routing between different networks. Then the fourth layer for both is the transport layer. This is, your TCP, UDP type protocols. And then here is where things get different, because in the OSI model, the fifth layer is the session layer, which this is just included in the application layer in the TCP/IP model, but this is where managing connections between applications comes into play. So if you're writing your own server, for instance, managing how you manage connections is a key part of how you implement your application. And the OSI layer model basically says that's its own layer of the network. Then the next one after that is the sixth layer, which is the presentation layer. This is how data is formatted if you're using data encryption. So this is like how you architect, how you send data to and from the server, for instance, how do you manage your API kind of a thing. Or I guess how you present the data to the user, probably through some kind of API, which again, on the TCP IP model, that's just a part of the application layer. And then the last layer in the OSI model is, guess what? The application layer. And this is, what provides the actual application to the end user. But again, all those last three are just roped up into the single application layer in the TCP IP model. So I guess this also kind of begs the question of why the TCP IP model is more widely adopted. Well, kind of as we touched on, the OSI model is more, theoretical, and it was really developed before the internet was widely adopted. And don't get me wrong, it's a very good theoretical model, but it's kind of a little too complex and cumbersome for real world implementation, specifically when it came to the internet. And the TCP IP model, on the other hand, kind of as we touched on, was developed alongside the internet, specifically the ARPANET, and was directly tied to the protocols that were being developed with the development of, the internet. So it kind of made sense that they kind of, I guess grew and developed in unison with one another. So it made it was a lot more closely aligned to the needs of what the internet needed, rather than just kind of this theoretical description for how the internet should operate. And the other thing too, at this point, the TCP IP model has been around for so long with the internet that it's basically the de facto standard at this point. And when basically everyone uses this thing, it's kind of hard to get everyone to change. Because even if you wanted to change the standard that's been the standard for decades, it would be a very, very, very slow process to get every single person on board, because chances are maybe not every device that exists, but there's going to be a lot of code that has to get rewritten. Probably some devices are just going to turn into bricks because they wouldn't be able to operate on the new networking standard. How do you handle those devices? Do you just say tough luck? Do you have some kind of, legacy support for the TCP IP model? But then if you had legacy support, what's actually forcing people to update to the new OSI model? It's a whole mess. TCP IP is here, and that's probably what's going to be here till the end of time. So yeah, the OSI model, kind of as kind of a summary, was basically, it's good for historical reference and really understand and break down how networks in theory should be designed and implemented, whereas the TCP IP model is more simplified and more adapted to how the internet actually works and how things actually happen. So one way I guess you could think about this is the OSI model is basically like the blueprint, whereas the internet and the TCP IP model is actually how it was constructed. So the OSI model is basically the blueprint for the internet, but, no matter how well you plan something out, things don't necessarily always going according to plan, and you run into issues, hiccups, and roadblocks along the way. So you kind of have to make some on-the-fly decisions to change things up a little bit, and then the end result doesn't actually match up exactly one-to-one with your original plan. But that's not necessarily a bad thing. That's okay as long as the end result actually works, I guess. And you still have the same general idea. For instance, if you're building a house based on blueprints, maybe you run into something when you were originally designing the house. I don't know, maybe there's like a massive boulder or something, or there's some kind of like line or something for either electrical, gas, or sewage or something that runs in such a way where you can't exactly stretch out this one corner as far as you wanted to, so you kind of have to jut it in a little bit. At the end of the day, you still have a built house. It just might not exactly line up one for one with the blueprint. But I mean, that's okay, because at the end of the day, it's still basically the house. It's what it is. But that's one way that you can look at it. So to do the final wrap up, to kind of recap everything, because we touched on a lot of information, I threw a lot at you today. So to kind of recap, I wanted to tie this back to a real world analogy, that being the post office analogy. So when it comes to the TCP/IP model, think of it like the post office. Think of it like sending a letter, and that's like sending data over the network. Basically, the TCP/IP model breaks down the process into different stages, which are basically the minor steps of sending the letter in the post office. So the reason why this analogy works and why it's generally fairly widely used is for one, segmentation and reliability, since breaking up the letter into different smaller pieces. For instance, if you wanted to send a large package through the mail, you could divide it up into smaller packages, or if you had one large letter, you could divide it up into smaller envelopes, or I guess divide the thick letter into different envelopes and do it that way, just like you can do with network packets. You can divide up the packets into smaller ones and send those off that way. Addressing, just like you would send a letter, you have to write the address on the letter or the package. You have to address in the networking layers as well in order to make sure things get to the correct location. And then reliability, the post office is pretty good at making sure that your mail arrives safely when it gets to you, just like the networking layers have to do the same as well. So starting at the top and then working our way down, since we kind of went from the bottom up when talking about the actual layers themselves, now let's go from the top down, because fun fact, that's kind of how it works. You have to, if you're starting at the application layer, you have to go all the way down to the bottom to the physical layer, and then in order for the application layer on the other end to receive it, it has to go back all the way up the stack. So we're basically kind of doing the same thing here, sort of. So application layer, this is you're writing the letter and whatever you want to say. So this is you, the writer, and the envelope itself. You're writing your actual message, which is basically the data, and crafting it into a format, that being the letter, and then you put it in the envelope. The envelope is basically the format that you're going to send the data off in, and then the letter itself is the actual data that you want to send. Then we get to the transport layer, which is essentially the postal worker and the reliable delivery. So this is essentially the postal worker taking your letter and then basically ensuring that it arrives safely to the correct location. Because like most things, if you're doing networking for reliability reasons, you're going to use TCP, which basically guarantees reliable delivery. And this kind of resembles, the postal service. They're going to basically ensure that your letter gets where it's supposed to go. Then you have the networking layer, which is basically the route, the postal service's routing system. Kind of as we touched on, this is where the postal service basically determines the best route for your letter to get from point A to point B. And then this is kind of, if you think of it like the IP address is whoever you're sending your letter to, it's their actual address in terms of the post office. So whatever address you put on the letter, that would essentially be like their IP address. And what the post office looks at that to determine where they need to route the letter to in order to get it to the regional sorting facility in order to then go for final distribution. And then that's where we get into the data link layer. And this is, again, kind of like the address on the letter. But kind of as we touched on, where the IP address is kind of like your city or your state where you live in. The MAC address is your physical street address where you live. So once the packet gets to the regional distribution facility, then it goes out on the mail truck, and the mail truck goes to your actual address to deliver the mail to you. And then, of course, the physical layer, that would be, the mail truck itself, or in the case of networking, that would be, the physical cables or, radio waves or whatever that's actually doing the transmission of the data. So just like a letter going through the postal service, there's several stages that it has to go through in order to reach its destination. And similarly, data has to travel through the TCP/IP model through each one of the different layers, which perform different functions on it. Adding different portions to the packet, whether that's the data, the error correction, the MAC address, the IP address, whatever the case may be, and basically ensuring reliable and efficient communication across the network. So yeah, we have gone kind of way over on time, but I wanted to make sure we covered everything. So yeah, let me know what you think about all this. I know this was a lot of information, but it's definitely very important information, like I said at the beginning, especially if you're anywhere in the IT field. But if you're not in the IT field and you're just kind of your average Joe, hopefully this gives you a better understanding of what's going on when you're, connecting to the internet or browsing the web or doing anything like that. But before we go, let us get back to our trivia question for the week, which, if you'll remember, there was a hint that I gave in the beginning that if you were listening closely, you should be able to do some math right about now in order to get this trivia question correct. So let's see if you guys can get it. And this week's trivia question, of course, is the IPv4 addresses are 32-bit numbers consisting of 4 8-bit octets. IPv6 addresses, on the other hand, are much larger and combine 2 octets into one to form a 16-bit hextet. How many hextets are there in an IPv6 address? So again, how many hextets are there in an IPv6 address? And if you said 8, congratulations, you got this week's trivia question correct. Or maybe you just are savvy with math and you realized if you divided, 128 with 16, 128 with 16, you would get 8. There you go. Congratulations. And that's going to do it for this week's episode. So if you enjoyed, definitely be sure to share it and leave it a rating and review, and subscribe if you haven't done so already. And also be sure to share this around with any of your friends, family members, anyone interested in networking. And also, if you have any questions about this episode, because I know we touched on a lot, or if you have any topics or ideas or comments for future episodes, definitely be sure to either leave a comment below if you're on YouTube, or you can shoot me an email at contact@darkassassinsinc.com. The link for that is down in the show notes below. And that's going to do it for me in this episode of the Dark Assassins podcast. Until next time, my fellow assassins, remember, bull nothing equals true. If action not equal to null, return true. I'll see you next time on the Dark Assassins podcast.